Okay, let's dive right in. It's really kind of mind-blowing how far AI image generation has come, isn't it?
Oh, absolutely.
We've gone from these like blurry, abstract messes to images that seriously look like they could win photography awards.
Yeah.
And at the heart of this whole artistic explosion are these things called diffusion models. You can think of them as, I don't know, super talented digital chameleons. They can paint pretty much anything you describe with words.
They really can. And the sheer complexity, the brain power packed into these models is staggering. We're talking billions of tiny adjustable knobs or, parameters, as the tech folks call them.
Billions.
Yeah, billions. And the more knobs, the more control you get over the final image, sure. But it also means these models become enormous. It's like trying to run, I don't know, the latest graphic software on a pocket calculator.
Huh. Exactly. Which brings us actually right to the core of our deep dive today. You, our listener, you're probably wondering, okay, how can we make these incredible AI artists even better, but also like faster, without needing a supercomputer in your basement?
Right.
So consider this your backstage pass, your shortcut to understanding a really clever new trick in the AI world.
And that trick, yeah, it comes from some brilliant minds who've really tackled this challenge head on. How to make these AI giants more, well, nimble.
Nimble, I like that.
We're going to be exploring a fascinating piece of research. The title is SVDQuant, Absorbing Outliers by Low-Rank Components for 4-Bit Diffusion Models.
Okay, wow. That's quite a mouthful.
It definitely sounds like something a robot would say after maybe eating a dictionary, yeah. But the underlying idea is surprisingly elegant and incredibly useful.
So think of this paper maybe as a secret recipe, like making a gourmet meal, but with a much smaller kitchen and way less cooking time.
That's a good way to put it.
Because these diffusion models, right, they produce stunning visual feasts, no doubt. But they are also massive resource hogs. They just gobble up computer memory and processing power like crazy.
They really do.
Which means waiting. Lots of waiting. And in today's world, I mean, waiting for your AI masterpiece to appear, it's about as fun as, well, watching paint dry.
Precisely. So our mission today is basically to pull out the most valuable, the most easy to digest insights from this research.
Well,
we want to explain what SVDQuant is, how it, pulls off its magic act, and maybe most importantly, how this could really be a game changer for anyone who's dabbling in AI image generation, whether you're a coding wizard or just someone who enjoys, turning weird text prompts into even weirder images.
Okay, so these diffusion models, they're like these massive, super intricate clockwork devices, capable of incredible stuff, but also, yeah, super clunky. Need a whole room to operate, kind of.
That's a spot-on analogy, yeah. And the trend in AI image generation, it has been to build bigger and bigger clocks, essentially, to get even more precise timekeeping, or in our case, higher image fidelity.
Right.
You mentioned Stable Diffusion 1.4 that had, around 800 million of those tiny gears, those parameters?
Which sounded huge at the time.
It did. Then came SDXL with a whopping 2.6 billion. And now we see models like FLUX.1 boasting, an astronomical 12 billion parameters.
12 billion, wow.
It's like this technological arms race, really, or more complexity to achieve these truly breathtaking results.
Which is fantastic, obviously, for pushing the boundaries of what's visually possible. But maybe not so fantastic if you're just trying to quickly whip up an image on your laptop while you're, say, brainstorming a new logo design or something.
Exactly.
You don't want to wait an eternity for one single image to materialize. You want something closer to, I don't know, instant gratification, like your own personal AI art vending machine.
That's the dream scenario, isn't it? To have this immense creative power just readily available on the devices we use every single day, and crucially, without them sounding like a jet engine is taking off in your office.
Yeah, definitely don't want that.
And that's where this idea of making things smaller comes in, a process known generally as quantization.
Quantization, huh? Sounds a bit technical. Like trying to fit a giant marshmallow into a tiny matchbox.
Yeah.
So in the AI context, what does that actually involve?
Well, think of it this way. AI models, they work with numbers, right? Often incredibly precise numbers, lots of decimal places. Quantization is basically like rounding those numbers, maybe to the nearest whole number, or sometimes even fewer options than that.
Okay.
It's a way of compressing these models, making them smaller by using less precise representations for those numbers. Imagine describing someone's height. You could say 5'10" and, 38ths of an inch, or you could just say roughly 5'10", or maybe even just 6 foot.
Right.
You lose a tiny, tiny bit of accuracy, maybe, but it's much simpler to remember, to work with.
Okay, I think I get the gist. Fewer decimal places, smaller numbers, means smaller file sizes for the model, and faster calculation.
That's the core idea, yeah.
But doesn't that mean you lose some of the, I don't know, the fine details in the AI's art? Like you end up with a slightly blurrier image or maybe less nuanced.
That is the crucial trade-off. Absolutely. If you reduce the precision too much, it's like trying to paint a masterpiece with only, say, 4 basic colors. You're just going to lose a lot of subtlety.
Okay.
And for these diffusion models to really, zip along on current hardware, the time we have in our laptops, we need to shrink both things. The model's weights, those are the billions of parameters, the knowledge, and the activations.
Activations, what are those again?
That's the data the model is actually crunching while it's generating the image, sort of its working memory during the process. Both of those need to go on a serious diet.
So it's like a double whammy. You're trying to make 2 already incredibly complex things smaller, all while trying not to mess up their artistic flair.
This sounds tricky, like trying to perform brain surgery wearing oven mitts.
Huh. It's a very delicate balancing act, yes. And that's precisely where SVDQuant kind of struts onto the stage. It offers a rather ingenious solution to squeeze these models down to just 4 bits.
4 bits.
4 bits, which is an incredibly aggressive level of compression.
Yeah.
Think fitting a grand piano into a suitcase. But the key is they try to do it without sacrificing too much of that vital image quality.
4 bits. That sounds ridiculously tiny. How on earth does it manage that without the images looking like, I don't know, they were drawn by a toddler with a blunt crayon?
Well, the secret sauce, as they say, lies in how it deals with what the researchers call outliers in the model's data.
Outliers. Okay, like extreme values. Exactly. Think of these outliers as unusually large, attention-hogging numbers. They're really difficult to represent accurately with such low precision, like 4 bits. It's like, imagine a classroom full of pretty well-behaved students, right? But then you have maybe 2 or 3 kids who are just constantly shouting, throwing paper airplanes, basically disrupting everyone else. Those are your outliers.
Okay. So these outliers are the troublemakers in the data. They cause chaos when you try to just squash everything down uniformly.
Precisely.
So what's the SVDQuant approach? How does it wrangle these unruly values?
Instead of trying to force these outliers to behave like all the other numbers, which, as you said, risks a massive drop in quality, SVDQuant uses a special low-rank branch. It essentially gives these outliers their own VIP section.
A VIP section for numbers. I like that.
Yeah.
Think of those shouting kids again. Instead of just trying to silence them along with the rest of the class, you give them like a separate room, maybe with some soundproofing and padded walls, plenty of space to burn off energy.
Oh, so they don't disrupt the learning, the main process happening in the main classroom.
Right. So you isolate the troublemakers. It's like creating a designated play area for these problematic outliers. How does this absorption, as they call it, actually happen, like under the hood?
It's quite a neat 2-step process, actually. First, SVDQuant subtly nudges the data around. It moves these outliers from one part of the model, the activations, remember the working memory where data is actively processed, over to another part, the weights, those more stable long-term parameters of the model. Think of it as gently escorting those energetic kids from running around the desks to a more contained area, like the back of the room, maybe.
Okay, so the activations become a bit calmer, more well-behaved, but now you've got these outlier numbers concentrated in the weights, right? Doesn't that just move the problem? How does the low-rank branch deal with that?
This is where the mathematical wizardry comes in, specifically something called singular value decomposition, or SVD. It's a technique, a mathematical tool that helps break down a big, complicated matrix of numbers, in this case, the weights, into simpler, more manageable components. SVDQuant uses it to create this small, but importantly, high-precision, low-rank branch.
High precision, Pat.
Yes, and that branch is specifically designed to handle these concentrated outliers with care. It keeps their precision. The rest of the model, the main part, which they call the residual, well, that's now much cleaner. It doesn't have those extreme values throwing things off.
I see.
So that part, the residual, can be quantized down to those super efficient 4 bits much more easily without causing chaos.
Got it. So it's like sorting a huge pile of mixed up Legos, maybe.
Yeah.
You first find all the really weird, oversized, awkward pieces. Those are the outliers you shift.
Yeah, good analogy.
Then, instead of trying to cram them into the regular storage bins with everything else, you build a special little, maybe stronger container just for those odd shapes. That's your low-rank branch using SVD.
Exactly. High-precision container.
Right. And this makes it much easier to organize the rest of your standard Lego bricks into their normal boxes. That's the 4-bit residual part.
Precisely. By isolating the outliers and giving them their own special high-precision handling, SVDQuant makes it possible to aggressively compress the vast majority of the model without, a catastrophic loss of image quality.
That's clever.
But here's where it gets even cooler because, just adding this extra branch, this extra calculation path could potentially slow things down again, right? More work to do.
Oh, yeah, I was wondering about that. It seems counterintuitive if the main goal is speed. Adding more complexity, how do they avoid that bottleneck?
You're absolutely right. That extra branch, that VIP section, it does involve more data wrangling, more calculations. That's where Nunchaku enters the scene.
Nunchaku, like the martial arts weapon.
Yep, exactly like that.
That's a surprisingly aggressive name for something designed to speed things up. So what is it? How does it manage this potential data traffic jam?
Nunchaku is SVDQuant's specially designed sidekick, basically. It's an inference engine. Think of it as a super efficient data traffic controller for the computation.
Okay.
It very cleverly orchestrates the calculations happening between the main low-bit part of the model and that special high-precision, low-rank branch. It fuses them together.
Fuses them.
Imagine you have two separate delivery trucks, one carrying the low-bit data for the main model and another carrying the high-precision data for the low-rank branch. Nunchaku is like replacing those with a single, incredibly well-organized truck with a super smart loading system.
Oh.
It figures out the most efficient way to combine the loads, to combine the calculations, and make fewer trips, essentially. A process the researchers call kernel fusion. It's all about minimizing the back-and-forth movement of data to the computer's memory, because that data movement is often a major bottleneck in these kinds of computations.
So instead of these two parts of the model running sort of independently and potentially getting in each other's way, Nunchaku makes them work together, like a beautifully synchronized dance.
That's a great way to describe it, yeah. A synchronized computational dance.
Okay, cool. So what kind of real-world speed improvements are we talking about then, thanks to this SVDQuant Nunchaku dream team?
The results they report are genuinely impressive. The research paper says that SVDQuant with Nunchaku achieves speedups of up to 8.7 times faster than the original uncompressed 16-bit model.
8.7 times.
Yeah, when they tested it on a standard laptop graphics card like an NVIDIA RTX 4090 laptop GPU, and even when you compare it to other methods for compressing these models, like one called NF4, which only crunches down the weights to 4 bits but leaves activations higher, SVDQuant is still significantly faster, around 3 times faster in some of their tests.
Wow. Okay, that's not just a little bit faster. That's like going from, I don't know, dial-up internet to fiber optic overnight.
It's a significant leap, yeah.
But we touched on image quality earlier. With all this aggressive shrinking, this 4-bit stuff, and the clever data management, how does SVDQuant make sure the generated images still actually look good? Is the quality really there?
That's where the real brilliance shines, I think. Despite this drastic reduction, remember 4-bit quantization for both the model's brain, the weights, and its working memory, the activations. SVDQuant does a remarkable job of preserving the visual quality.
Okay.
The researchers even include some compelling visual examples in their paper. There's a cyberpunk cat.
A cyberpunk cat. Love it.
And a medium rare steak, which, by the way, it looked surprisingly appetizing even in its compressed 4-bit form. And in these examples, the 4-bit SVDQuant results are visually virtually indistinguishable from the original, much larger 16-bit versions.
Okay, a cyberpunk cat and a mouth-watering steak. Those are definitely memorable benchmarks. The paper also mentions these things called LPIPS scores. What are those exactly? And what do they tell us about how good the images actually look beyond just, our gut feeling?
Right, LPIPS. It stands for Learned Perceptual Image Patch Similarity. It's basically a fancy metric, an algorithm, that tries to quantify how similar two images appear to a human eye.
Okay. So it's trying to measure similarity the way we see it.
Exactly. Think of it as a computer trying to judge if two pictures look alike in the same way we would. And with LPIPS, lower scores are better. They indicate that the images are more perceptually similar.
Gotcha. Lower is better.
And the paper demonstrates that SVDQuant achieves LPIPS scores that are not only significantly better than other attempts at full 4-bit compression, weights and activations, but in some cases they even rival or surpass methods that only compress down to 8 bits.
Even better than 8 bits sometimes. Wow.
Yeah. And they also provide visual comparisons in the paper side-by-sides, where SVDQuant's 4-bit images often look noticeably sharper, more detailed than those produced by other low-bit techniques.
Okay, so it's not just about making things fast. they've genuinely managed to do it without making the AI's artwork look, well, bad, or like it was painted on a postage stamp.
Right. They found a way to balance speed and quality remarkably well.
So, okay, let's bring this back to you, our listener. You might not be a card-carrying member of the AI fan club. Maybe you don't care about bits and LPIPS scores. What are the tangible benefits here? What are the potential real-world applications of a technology like SVDQuant? Why should this make your ears perk up?
This is where the excitement really kicks in, I think. Because even if you have zero desire to peek under the hood of an AI model, SVDQuant has the potential to significantly impact your work, maybe even your daily life.
How so?
Well, imagine being able to generate high-quality custom images much, much faster on your own laptop or maybe even tablet without needing to rent time on some expensive cloud computing service. That just unlocks a whole new realm of possibilities, doesn't it?
Yeah, it really does. Like what specifically? Give us some concrete examples of how this could change things for, regular folks.
Okay, well, think about content creators. Marketing folks, social media managers, they could rapidly generate marketing materials, eye-catching posts, or even just find visual inspiration way faster than they can now.
Right, less waiting for variations.
Exactly. Or designers, they could quickly prototype different ideas, visualize concepts for clients right there on the fly. In education, imagine creating really engaging visual aids or interactive learning experiences that actually run smoothly on more affordable hardware in schools.
Interesting.
And even for accessibility, this could lead to more efficient tools for visually impaired individuals who rely on image descriptions or perhaps even generating alternative visual representations.
That's a great point.
The big aha moment here, I think, is that a technology that was once pretty much confined to powerful servers and research labs, well, it could become a practical integrated tool in our everyday digital lives, much more democratic.
That paints a really compelling picture. AI image generation becoming less of this niche, high-powered thing and more like an accessible creative companion.
Yeah.
For potentially everyone.
That's the potential, yeah.
And the researchers also point out that SVDQuant is quite versatile, right?
Yeah.
It has potential for future development.
Absolutely. It's designed to be compatible with various types of diffusion model architectures, things like UNets and the newer transformers or DITs. So it's not just tied to one specific brand of AI artist, so to speak. And it also plays nicely with LoRa's.
LoRa's. Right. Those are like style add-ons.
Exactly. Low-rank adapters. They're like small plug-in style packs that let you fine-tune a base model like Stable Diffusion to create images in specific artistic styles, maybe anime style or photorealistic, whatever, without having to retrain the entire massive network each time.
Okay.
And what's particularly neat is that SVDQuant can efficiently incorporate these LoRa's without needing to be requantized or reoptimized every time you add one.
Well, that's handy.
Yeah, it gives users a huge amount of flexibility, customization, style transfer. The paper even shows examples applying different artistic filters to images generated with their fast 4-bit model.
So you could have your super fast, memory-sipping AI image generator and then just easily plug in different artistic personalities on top without any extra hassle or slowdown. That sounds incredibly user-friendly.
It really lowers the barrier to experimentation and customization.
And it seems like the research in this whole area, model compression and efficiency, is just moving at warp speed still.
Oh, indeed. This paper we've been discussing, it's actually the finalized version for an upcoming conference, I think CVPR 2025, and it includes even more recent advancements they've made since the first draft.
Like what?
Well, they've been exploring combining SVDQuant with another cutting-edge optimization technique called GPTQ, which promises to squeeze even more performance out of these models.
Wow, okay.
It's a testament to the incredibly rapid pace of innovation in AI right now. Things change month by month.
All right, let's try and wrap up our deep dive then. If you had to boil it down, what's the single most valuable takeaway from all this talk about SVDQuant?
I'd say the key insight is this. SVDQuant represents a really significant breakthrough in making powerful AI image generation faster, much more memory efficient, and ultimately way more accessible to a wider audience.
Okay.
And it achieves this remarkable feat by, well, cleverly addressing the inherent challenges of doing extreme 4-bit compression. It uses that innovative low-rank branch for handling the problematic outliers, and it has its co-designed inference engine Nunchaku to make sure there's minimal performance overhead from that extra branch.
Right.
Essentially, it's about making these incredibly complex AI tools more practical, more user-friendly. Crucially, without completely sacrificing their creative power.
So it's not just about shrinking the models down blindly. It's about doing it intelligently, preserving that artistic quality while giving it some massive speed boost.
Exactly.
And this really could, as you said, democratize AI image generation, making it a tool potentially for everyone, not just folks with access to high-end hardware or expensive cloud credit.
Precisely. And that leads to the really interesting question for everyone listening. Think about how faster generation times, lower hardware demands, wider integration into apps you already use. How could that fundamentally change the way you create, the way you communicate visually, maybe even the way you learn new things? What exciting new possibilities does this kind of efficiency unlock for you personally or for your work? That's a really compelling question to mull over, I think.
That is a fantastic point to leave our listeners with, a real provocative thought. If you were intrigued by all of this, you could definitely, search online for terms like diffusion models or neural network quantization. See where it leads you, and who knows, you might even stumble upon the open-source SVDQuant library and that Nunchaku inference engine the paper mentions. See it in action, maybe even try it out if you're technically inclined.
Yeah, the code is out there.
It's truly exciting to contemplate how these technologies will just keep evolving and shaping our digital landscape in the coming months and years.
It really is. The relentless pace of innovation in AI is, well, kind of inspiring, isn't it? And these ongoing efforts to make these incredibly powerful tools more readily available, more democratic, that's what really drives progress. SVDQuant is just a shining example of that ingenuity, making something that seemed almost impossible just a short while ago.
Well, a step closer to everyday reality.